So some factors that influence the stability of resonance structures. So there are some factors that make some resonance structures better than other resonance structures. So a big one is charge. Okay? This could be positive or negative charge. Okay? So here we do have a valid resonance structure set up here, because the pi electrons can go up onto the oxygen, causing the oxygen to be negative and the carbon to have a positive charge. Okay, this is correct. Okay, the overall net charge is the same. Here the overall net charge is 0, and in this structure the overall net charge is 0. So this is a valid resonance structure. However, one of these is more stable than the other. The one on the left is more stable than the one on the right because of this charge separation and the fact that we have charges on atoms. Remember, atoms want to be neutral. So, when you have two different or even more resonance structures, when you have more than one resonance structure, if they are different in energy, okay, so this is more stable, which means it's lower in energy, okay. So when you have more than one resonance structure and they are at different stabilities and different energy levels, you will have what's called a major contributor and a minor contributor, okay. So the more stable the resonance structure is, the more of a contributor it is to the hybrid. Because remember, in the last video we said only the hybrid exists. Okay, so the hybrid of these two resonance structures looks a little bit like this one and a little bit like this one. But because this contributor is more stable, the hybrid actually looks more like this structure than it does this structure, okay? And so what we do is we say that this is the major contributor and this one is the minor contributor, okay? So other things, factor 2 is the octet rule. Okay, so here, let's use a different color. Here we have 3 different resonance structures. Okay, so here this goes there. Now there's a positive charge there. Then one of the lone pairs drops down. Now the positive charge is on the oxygen. Okay, so these are all correct resonance structures. Now which one of these is the most stable? Okay, well here the carbon has a positive charge, here this carbon has a positive charge, and here the oxygen has a positive charge. So a lot of times when we think of oxygen versus carbon with a positive charge, we would think that carbon is more stable with a positive charge because oxygen is more electronegative. If oxygen is more electronegative, then it would prefer to be negative rather than positive. And carbon is not that electronegative, so it doesn't really care. And that's a good way of thinking about it, but there's something that's more important, which is the octet rule. So even though oxygen doesn't want to be positive, okay, of course carbon doesn't want to be positive either, but if you look, when oxygen has a positive charge, it has a complete octet. But when a carbon has a positive charge, it does not have a complete octet. And having an octet is very stabilizing for atoms. So it's very important to have an octet. So when you're looking at this, the octet rule is very important, okay? So this oxygen, let's actually look. We know that it has an octet because we have one lone pair. So 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has an octet. Okay, so this molecule right here has octets on all of its atoms, whereas these other two molecules, we have octets on all of the atoms except for one, the carbocation. So this molecule, I should say these molecules, this one and this one, do not have octets on all of their atoms. Okay, and because of that, that means that these two molecules right here are less stable and therefore are minor contributors. And this molecule is the major contributor because it's the most stable. Wow, I am writing pretty bad. So it's the most stable, and therefore it's the major contributor. Okay, then we have electronegativity. Okay, so here we have two resonance structures for this molecule. A negative on a nitrogen, and if this comes up here and that moves right there, then we'll have a negative on the oxygen. So all of the atoms have octets, so that's not a factor here. The factor here is we have a negative on a nitrogen versus a negative on the oxygen. Which structure, A or B, is more stable? Well, what's more stable, having a negative charge on nitrogen or having a negative charge on oxygen? The answer is oxygen, because oxygen is more electronegative. So oxygen is more electronegative and therefore can hold a negative charge better. Okay, it's more stable when holding a negative charge than when nitrogen's holding a negative charge, which means that molecule B is more stable, which means that it is the major contributor. Whereas molecule A is a minor contributor. So the resonance hybrid will look more like B than it does with A. However, A still contributes some of the character to the hybrid, okay? All right, so these last two are just some practice, more practice with resonance. So I suggest that you pause the video and try practicing these by yourself, and then play the video and see how I run through it and compare it to what you wrote. So here we have a negative charge. So when I see a negative charge, to help me out, I think a lone pair to bond forces a bond to a lone pair. So here's my lone pair, and I'm going to force it into the bond that it's right next to, which means that this pi bond has to go on to this carbon atom. So I now have a lone pair there, making that carbon a negative formal charge, and I have that pi bond. Now I didn't touch these two bonds, so they're still where they were in the beginning. I'm going to use this color. All right, so can I move this lone pair now? Well, yes, I can take this lone pair and move it into a bond, which forces a bond to a lone pair. So now my molecule looks like this. And again, can I move it again? Well, yes, I can. So I can take this lone pair to bond, forces a bond to the lone pair. So now my molecule looks like this. Now, can I move this lone pair anymore? No, there's no other place I could move it. I could go back, but I've already drawn those resonance structures, so there's no need for me to draw them again when they're already drawn, okay? I've already accounted for those resonance structures. So here are the 4 resonance structures for the molecule given. So the next one, we have a positive charge. And so when I am doing resonance with a positive charge, I like to think of opening the door of a pi bond towards the positive charge. So I can do that, which means my positive charge is now here. Can I move it again? Yes, I can. I can move that there, which means my positive charge is now on that carbon. And I can move it one more time, which means my positive charge is on that carbon. So those are the 4 resonance structures, and the way that I get to all 4 of those resonance structures for the carbocation in the molecule.